Hi, welcome back to the Differential Equations lectures here on Educator.com. My name is Will Murray, and today we're going to study Euler equations. So let's jump right in. Euler equations have a very special form. They're of the form x squared y double prime plus a constant, which I'm calling alpha, times xy prime plus beta, another constant, times y is equal to 0. The idea there is that there's this pattern of descending powers on the x. So this is very important. We got x squared here, we got an x here, and you want to think of this as x to the 1, and think of this as x to the 0 because it's just a constant. So you really have to have that exact pattern of the powers, x squared, x, and x to the 0, in order to make the Euler equations work. If you do have that pattern, then there's a very easy solution. It's basically x to the r, but let me show you how you figure out what r is. So what you're going to do is you're going to solve the characteristic equation for r, and there's a little subtlety here. Basically, you take the coefficients from the Euler equation, but there's a small change, which is that instead of just taking alpha and beta, you take alpha minus 1 and beta. So you solve this characteristic equation, r squared plus alpha minus 1 r plus beta is equal to 0. And that's just a quadratic polynomial. So you can solve that by factoring. You can solve that by the quadratic formula. Whatever works for you to solve that. And you'll get two roots for r. So you get an r1 and an r2. So this isn't very hard. This is just algebra. You could get two real roots, so you could get like r1 equals 3 and r2 equals 5 or something like that. You could get one repeated root, meaning you get a double root, or you could get two roots that are complex conjugates, something like a plus bi and a minus bi. That's if you run the quadratic formula and you get a negative number under the square root sign, then you're going to get two complex conjugate roots. So let me tell you what to do in each one of those situations, how you write down the solution to the differential equation. If you have real distinct roots, meaning two different real roots, the general solution to the equation is just x to the r1 times a constant and x to the r2 times another constant. So it's really very easy there. If you have repeated roots, so the same copy of the root appears, you have x to the r1 and x to the r1 times natural log of x, again multiplying each one by a constant. And if you have complex roots, then it'll always occur in conjugate pairs, remember, because remember the quadratic formula is something plus or minus the square root of something, and so if you get a negative number under the square root, then you'll end up getting a conjugate pair, something like a plus or minus bi. And it's a little more complicated if you do that, but it's just a formula to remember. It's x to the a times cosine of x of log of x to the b, and x to the a times sine of natural log of x to the b. So those are your two fundamental solutions, and you just multiply each one by an arbitrary constant, and you get the general solution. So that's pretty much all you need to know for Euler equations. You solve the characteristic equation, get the two roots, and then just depending on which of these three situations it is, you just drop it into one of these three formulas. So let's try that out with some examples. In our first example, we want to find the general solution to x squared y double prime minus 3xy prime plus 3y is equal to 0. So we've got this Euler pattern on the coefficients, x squared, x, and then a constant here. So it is an Euler equation. And the alpha here is negative 3, because that's the coefficient here. The beta is 3. And remember, the characteristic equation is always r squared plus alpha minus 1 r, alpha minus 1 r, plus beta is equal to 0. So that's the equation that you always solve for r. And so in this case, we have r squared. Now, alpha is negative 3, so alpha minus 1 is negative 4. So this is actually minus 4r, and beta is 3, plus 3 is equal to 0. Now, that equation factors quite nicely. That's r minus 1 times r minus 3 minus 3 is equal to 0. So our two values of r are 1 and 3. r equals 1 and r equals 3. And so now we can drop those right into the general solution. The general solution is c1 times x to the 1. So I'll just write x, but that's really coming from x to the 1, plus c2, x to the 3, or x cubed. And that's it. That's our solution to the differential equation. So it's really a nice relief that these Euler equations are much easier than some of the other things we've been doing recently, like series solutions. Let me recap quickly how we worked that out. We noticed that this was an Euler equation because it has that descending pattern of powers, x squared, x, and constant. So we read off our values of alpha and beta, just the coefficients there, negative 3 and 3. Drop them into this characteristic equation. The key point there is to remember to subtract 1 from the alpha. So we get r squared minus 4 plus 3 equals 0. Factor it out, get our roots, and then those become the powers, and we get our general solution. So let's go ahead and try another one. We still have an Euler equation here because the powers on x are descending. So we have x squared and x and a constant. And so our alpha here is negative 7. Our beta is 16. So we're going to use our generic characteristic equation, r squared plus alpha minus 1r plus beta is equal to 0. So our alpha is negative 7, so alpha minus 1 is negative 8. Minus 8r plus 16 is equal to 0. That factors into r minus 4 squared is equal to 0. So we get the double root at r equals 4. r equals 4 or 4. So we had a different formula for when we have a double root. The general solution, c1 x to the 4th, but we can't have a c2 x to the 4th because that would just be a copy of our first solution. So c2 x to the 4th natural log of x. We got that straight from the lesson overview at the beginning. Whenever you have a double root, that second solution, you just multiply it up by natural log of x. So that's the end of that one, but just to recap, we noticed our descending powers of x, x squared, x, and constant. That's what triggers you that it's an Euler equation. Write down your alpha is the coefficient of the first, beta is the coefficient of the second one. Plop those into our generic characteristic equation where you have an alpha minus 1, so that negative 7 turns into negative 8. Factor it out. Once you get a double root for r, you know one of your solutions is x to the 4th, but the other solution, in order to get an independent solution, you got to multiply it by natural log of x. That's our second independent solution there. Our next example here, again, we have an Euler equation. We can check that by noticing the descending powers of x, x squared x, and a constant there. So we've got the descending powers of x. We've got an Euler equation. Our alpha here is negative 1. Our beta is 5. So those are the values we're going to use in the characteristic equation, r squared plus alpha minus 1, r plus beta equals 0. So if alpha is negative 1, then alpha minus 1 is 2, and beta is still 5. Now, that thing does not factor, so we're going to jump to the quadratic formula to solve that. Remember, the quadratic formula says negative b plus or minus the square root of b squared minus 4ac over 2a. So here our negative b, well, our b is negative 2, so our negative b is positive 2. Plus or minus b squared is negative 2 squared, so that's 4. 4ac is 4 times 1 times 5, so that's 20. 4 minus 20 over 2a is 2. So that's 2 plus or minus 4 minus 20 is negative 16, so the square root of negative 16 is 4i. Going to get complex roots here, complex roots, and that simplifies down to 1 plus or minus 2i. Now remember, we had a generic solution formula when you have complex roots. The generic solution formula was, let me remind you what that was from the lesson overview at the beginning of class. C1 x to the a times cosine of natural log of x to the b plus C2 x to the a times sine of natural log of x to the b. You could also use your natural log rules and write this as b natural log x inside. That would be okay if you like that better. And the a and b here, they're not the a and b from the original equation, so be quite careful about that. That's the a and b come from the a plus or minus bi here. So it's not the same as these a's and b's that we used in the quadratic formula. Be very careful about that. So what we have here is our general solution. C1 x to the a, our a is 1, so I'll just write x, times cosine of natural log of x to the b, b is 2 here, so natural log of x squared, plus C2, same thing with sine, x times sine of natural log of x squared. And that's our solution. So let's take a look and see how that worked out. We had our Euler equation because of those descending powers of x, x squared, x, and a constant. So we read off our coefficients. Alpha is negative 1, the coefficient of the x term. Beta is 5. And we plug those into the characteristic equation. Remember the subtlety where the characteristic equation, you drop the alpha down by 1. So alpha minus 1 becomes negative 2. The beta is 5. And now to solve that, we have to go to the quadratic formula. And that simplifies down to 1 plus or minus 2i. And so we use that as our a and b, not the a and b for the quadratic formula, but the 1 and the 2 are the a and b that we're going to plug into our generic solution for Euler equations when you have complex roots. So we plug in x to the 1 here. We get x cosine log of x squared and x sine log of x squared as our two independent solutions, and we put them together with constants to make our general solution. So for example 4, we've got x squared y double prime minus 6xy prime minus 12y is equal to 0. Again, we check out first that this satisfies the properties of being an Euler equation, those descending powers on x, x squared, x, and a constant, x squared, x to the 1, x to the 0. Remember, it's got to fit that format exactly to be an Euler equation. If it doesn't fit that format, then you're really out of luck. You got to use some other technique, which will almost certainly be more complicated. So it's worth checking if something is an Euler equation. If so, these things are really pretty quick to solve, but if not, then you're going to have to do something that's probably going to be much more lengthy. So since this one does work, we read off our alpha is negative 6, our beta is 12, and we set up our characteristic equation, r squared plus alpha minus 1, r plus beta is equal to 0. So that's r squared. Alpha was negative 6, so alpha minus 1 is negative 7. R plus 12 is equal to 0. That's another easy one to factor. That's r minus 3 times r minus 4 is equal to 0. So our r is 3 or 4. So two distinct real roots. That's kind of the easiest situation for an Euler equation. Right away, I can write down my general solution. It's just c1 x to the 3 from that first root plus c2 x to the 4th from that second root. And just like that, we're done with that one. So let me remind you of how that one worked out. We first checked the powers, x squared, x to the 1, x to the 0. Looks like an Euler equation. So that means I can write down the coefficients. Alpha equals -6, beta equals 12. Drop them right into my characteristic equation, which has that shift of the alpha down by 1. So we got r squared minus 7r. That's alpha minus 1. Plus 12 equals 0. Factors nicely, gives me a couple roots. And those roots become the exponents on x for the general solution. So in example 5 here, again we've got an Euler equation because we recognize this descending power of x's, x to the 2, x to the 1, and x to the 0 here. No x at all means x to the 0, or x to the 0 you think of as being a constant. So I can read off my coefficients. Alpha is 5. Beta is 4. So I'm going to set up my characteristic equation. It always has the form r squared plus alpha minus 1 r plus beta is equal to 0. Remember to shift that alpha by 1. This is a subtlety of Euler equations that we haven't really seen anywhere else. So in this case, the alpha is 5. So we get r squared plus 4r plus 4 is equal to 0. So that first 4 here, this one right here, that comes from 5 minus 1. It has nothing to do with beta being 4 there. And we want to solve that, but that's easy to solve. That's r plus 2 squared is equal to 0. So r is equal to -2, and that's a double root. And remember, we have a special formula for when you have a double root of an Euler equation. And that formula is, first you just have x to that power, c1 x to that power. But then you can't have c2 times x to that power again, because that would just be a copy of your first solution. And the way you get around that is you multiply on a natural log of x. So that's our general solution to that one. So let's recap how that problem worked out. We recognize these descending powers, x to the 2, x to the 1, x to the 0. Okay, that means it's an Euler equation. So we identify our alpha as the coefficient of the x term. Beta is our coefficient of the constant term. And then we go to our generic characteristic equation with an alpha minus 1 in it. And so we get r squared plus 4r plus 4. That's using alpha minus 1 to get that 4 right there. That factors easily into r plus 2 squared equals 0. And so that turns into r equals -2. So that's a double root. And so in the case of a double root, our solution is, well, just like with two distinct roots, we form x to that power, x to the -2. But then for the second one, we can't just form x to the -2. That would be a copy of our first solution. So we go x to the -2 natural log of x to give ourselves a distinct solution, and we put a constant on each one. So in example 6, we got the differential equation x squared y double prime minus 3x y prime plus 29y is equal to 0. As before, look at this, and we got x squared, x to the 1, and x to the 0. That means it is an Euler equation, so we can use what we've been learning in this lecture. So we're going to identify our alpha and our beta. Alpha is -3 here. Make sure you include the negative. Sometimes people will just see the 3 here, and they'll just say, okay, alpha is 3. And of course, that's going to lead you to disaster later on. So don't forget those negatives if they're part of it. Beta is 29. We'll go to our generic characteristic equation, r squared plus alpha minus 1 r plus beta is equal to 0. So alpha is -3, alpha minus 1 is -4. R plus 29 is equal to 0. And it'd be great if that would factor, but it doesn't factor easily. So we're going to go to the quadratic formula for that. So r is equal to -b plus or minus the square root of b squared minus 4ac over 2a. And in this case, our b is negative 4, so negative b is positive 4, plus or minus. Now b squared is 16, and 4ac is 4 times 29, 4 times 1 times 29, which is 116. And that's all divided by 2a, but a is just 1, so that's 2. So that's 4 plus or minus the square root of negative 100 over 2. Now, negative 100, the square root of that is 10i. So this is 4 plus or minus 10i over 2. So 2 plus or minus 5i. And we have a generic solution formula for when we get complex roots to the characteristic equation. It's c1 x to the a times cosine of natural log of x to the b plus c2 x to the a times sine of natural log of x to the b. You could also write that as b natural log of x. That would be correct. And the a and b, they're not the a and b from back here in the quadratic formula. They're the a and b that you got at the end. So that's that a and that b. So let me go ahead and plug those in. The general solution here is c1 times x squared cosine times natural log, cosine of natural log of x to the fifth, plus c2 x squared times sine of natural log of x to the fifth. You could write that as 5 natural log of x if you like. And so that's our general solution to this Euler equation. So let's go back and see how that worked out. First thing to do is recognize the powers, x2, x to the 1, and x to the 0. That's what you have to have for an Euler equation to work out, is those descending powers of x's. If you do, it's going to work out pretty easily. If you don't, you kind of have to abandon the Euler methods completely, and you just got to try something completely different. So we found that it worked out for this example. So we identify our alpha is the coefficient of the x term. Our beta is the coefficient of the constant term. And we go back to the generic characteristic equation, r squared plus alpha minus 1r plus beta is equal to 0. Our alpha was negative 3, so that's subtracting 1 from that is where this negative 4 came from. And we got this quadratic equation that really didn't factor nicely, so we used the quadratic formula. We got a negative root under the negative number under the square root, so we get complex numbers, 2 plus or minus 5i. And then we drop those as our a and our b, not the a and b from the quadratic formula, but our a and b from the complex number we found. We drop those into our generic solution formula for Euler equations with complex roots, which is x to the a cosine log b plus x to the a sine log of b, log of x to the b. And so we get c1x squared cosine log of x to the fifth, c2x squared sine of log of x to the fifth. So that's our general solution to the differential equation. So that's the end of our lecture on Euler equations. By the way, you might have come here looking for Euler methods, which is actually something quite different. That's something we're going to get to in a later lecture here on the differential equations lectures. So if you're looking for Euler methods here and this didn't look at all like what you were expecting, just scroll through and look for a later lecture on Euler methods. That's a numerical solution to differential equations. So you'll find that here on Educator.com. It's just this was a specific lecture about Euler equations. So that wraps everything up here. This has been the Euler equations lecture on in the differential equations series here on Educator.com. My name is Will Murray, and I thank you very much for watching. Bye-bye.